Okay, so this question has got three different parts that are working in with it. We've got a circular motion part, a projectile motion, and then this part over here for the acceleration of the motion of the little cart that's moving along. So when we're talking about circular motion, you can always look back at chapter or exercise 4.7 to refresh your mind about some of the formulas. But over here, we've got angular velocity is given by this symbol. T is given as the period in time, and from that we can work out a couple of different things. Now, once I've got that information, I can work out the speed by doing the angular velocity multiplied by the radius of the thing that it's being spun around by. So once I use those formulas, I can move on to the projectile motion part of this question. Now, normally you would get an angle and a speed. I can see from the circular motion part that I can still, in fact, get a speed. So after we come up with our formulas for projectile motion, we can use the speed from over here to input into here. Now, the next thing that I've got is that it passes through this point here, which is going to allow me to solve for the angle so that I can complete this question. Now, the last part is this bit down here for the motion of the cart, and that'll all fit together nicely. So let's get started. So first thing I'm going to do is I am going to use or apply this formula. So this is going to help me calculate the angular velocity of this thing. Now, this formula is given to you in simple harmonic motion in the formula booklet. So be aware of what's in the formula booklet. Even though this isn't a part of simple harmonic motion, that formula still applies. Now, from the question, I've got that t equals 0.24. So all I need to do is rearrange this to get w is equal to 2 pi over 0.24. So w is going to be equal to, now if you want to keep it in exacts, 25 over 3, or it will be 26.18 radians per second. Now, the next thing that we want to do is we want to calculate the actual speed. So now we're going to find speed or velocity. So v is equal to rw. Now, unfortunately, this isn't a formula that you get given. This is one of the ones that they just expect that you'll remember. Okay, so velocity is equal to 0.5, which is the radius that this thing is moving around by. 0.5 multiplied by our answer from over here, 26.18. So once you pop that in the calculator, that will give you an answer of 13.09 meters per second. Okay, so now I currently have my speed for this. So we're done with our circular motion portion of this. We're now calculating, if you think about this point here, that we're going to be calculating our projectile motion equations. So there are some notes that I wrote up for you guys. I printed them out. I handed them to you in class about projectile motion. It might be a good idea to go back over those before you start trying to do this question. But what we're going to do is we're going to find the equations of motion. Now, the first one for this is super simple, which is the acceleration one. Now, if we just think about how something flies through the air, acceleration is just given as gravity. So minus 9.8, traveling in the up-down motion, so it's a J component. If you're looking at the acceleration in projectile motion, here there is no I component for acceleration, only the J component. Now, the next one we're going to do is get our velocity or our speed function for this. So in order to do that, we need to think about it in terms of what it actually is. So I'm just going to draw a little diagram over here, just like we did in class. Now, we've worked out that the speed of this is going to be equal to 13.09. We also know that this is the angle that we would have. It's going off in that direction. So if you're thinking about this thing being released, its speed makes up this triangle here. So the I component of this is the adjacent side, and this is the opposite side. So to calculate the length of this will be 13.09 cos theta, and this one over here will be 13.09 sine theta. So we're going to be integrating our acceleration function, and we're also going to be accounting for those speeds. So Vt is equal to, our I component will be 13.09 cos theta I plus 13.09 sine theta. Now that J component also has this part. So we're going to integrate that portion too. So minus 9.8, and it gets a T on it. Because when we integrate it, we add on that variable. Okay, and that is its motion in the J direction. So next thing we need to do is we need to work out its displacement function. So RT is equal to the integral of the velocity function, and don't forget to add in any context that we have here. So when I integrate this part here, it's going to become 13.09 T cos theta I. Now, the reason why this cos theta doesn't have any change to it is because it's not the variable that's being adapted. If we were integrating with respect to theta, then this would have to become a sine function. But because we're integrating with respect to t, this acts just like a constant value, constant value. So it's just a number, it's just an ugly number, we just don't know what it is yet. Okay, plus 13.09 T sine theta minus 9.8 T squared divided by 2. Now, that is motion in the J direction still. Now, that would be fine to leave it like that, but this thing does have some extra context to it. So when we're looking here, you can see that this thing starts 0.3 meters above the ground. So this has been shifted by 0.3. The I component starts right on 0 here, so it doesn't need to be adjusted at all for that context, but this second part does. So therefore, our real function here can be represented by 13.09 T cos theta I plus 0.3 plus 13.09 sine theta minus 9.8 T squared over 2, close bracket, and that's all the motion in the J direction. Okay, so what we found so far is we found our equations of motion. I've now got an equation for the displacement of this thing. Now here, I've got a point that it is displaced by. So at some point here, at some certain time, it travels 14 meters in the I direction, and it travels 2.05 in the J direction. So that's what we're going to be using next to solve for our next part. Now I'm going to keep doing the working over here, and let's just hope it doesn't look like a hot mess express. Okay, so next thing we're going to do, we're going to use the coordinate x equals 14, y equals 2.05. So this comes under parametric equations. What we're going to be doing to solve it is I'm going to take the x component here, which is going to be equal to 14 equals 13.09 T cos theta. Okay, and we're going to use that to solve simultaneously, because the other equation we've got is that 2.05 is equal to all of this. So if I rearrange this to get it in terms of t, so t equals, all I have to do is gather up these other parts and take it under by dividing. Everything here is multiplying. It's 13.09 times t times cos this. So it's just going to become divide. Okay, so now I've got a function for t. Let's look at the y component. Okay. So next thing I'm going to do, chuck this in as t into this function. Let y equal 2.05 is equal to 0.3 plus 13.09 sine theta. That should have had a t in it here. Sine theta times 14 over 13.09 cos theta minus 9.8 divided by 2 times 14 over 13.09 cos theta squared. Okay, and that'll be our j component there. So you can do a lot of fancy maths to work this out, or you could use Solven. Now, if you're in your exams, we would expect that you would use Solven. We wouldn't be expecting you to do the algebra for this by hand because it would take too long. Solven is your sneaky little trick to get around that problem. So make sure your calculator is in radians. And once you put that in with Solven, the answer you will get is 0.64 radians. So now we've got our angle here. Now I could chuck this back in up here to work out the time that it crosses over that point, but we don't really care about that time that it crosses over. We need the angle so that we can start plugging it in and work out what this is as a number and use that answer carrying forward. So the next thing that we're going to be doing is we're going to solve for when it hits the ground. So if I just scroll back up to my thing, what I've got so far, okay, I've used this information. We found out everything we want from the projectile motion here, but what we need next is we want to know when does it touch the card or the time that it touches the card. We also want to know the displacement for when it touches the cart too. That'll be helpful later on. So if I can get those two variables, then I can solve this thing. So the next thing to note, if we're looking at this in terms of projectile motion, this goes like this, wee, book, and then it hits down there. Now, I don't know what the x displacement of that is, but I do know that the y, it has to be 0.4 meters high. So I'm going to use that as my fact. Maybe I'll do this just to the side here. Okay, so we're going to use the y component here. So we're going to let y equal 0.4, theta equals 0.64, and then I'm going to steal the rest of this equation here to solve for what it is. Sorry, this equation here to solve for its displacement at that point, or the time, sorry. Okay, so 0.4 is equal to 0.3 plus 13.09 t sine theta, which we're now going to replace with, so sine 0.64 minus 9.8 t squared over 2. Okay, so now that I've got this, again, Solven, save yourself some time. This is going to return to me the times that when it's at this value. So we get two answers for this. You get 0.01289 and we get 1.58 2. So the next thing you need to do is start thinking about which of these answers is going to be the correct one. Now, if you're thinking about your projectile motion, what's actually happening in the question, here you are. You release the ball, whee, goes up, goes down. Okay, your cart is over here, and it passes through 0.4 here and here. So this one here is when time is equal to 0.01289. And this one here is the one we actually want because that's when it's touching the cart. So therefore, we're going to let t equal 1.582. Now, the next thing that I'm going to need, and you're going to see why we need this later on, but I may as well calculate it now while it's all in the same. We're going to find the distance the cart's travelled. So I'm going to take this time and I'm going to take the angle that we found and I'm going to substitute it in here to work out when the time is there, when it touches the cart again, how far have we moved in the x direction. This is something we're going to need to work out the acceleration of the cart later on. So equals 13.09. Now we have an answer for what our t is. Remember, make sure your calculator's in radians, otherwise, boom, there's your problem. Okay, so once you do this, let's just punch it in the calculator to make sure I'm not going to get any rounding errors. I've been avoiding putting it into solvent and stuff in this video just to save you some time because sometimes inputting it takes longer than doing the actual question. Okay, so execute. So 13.09, 1.582 cos of 0.64, close bracket, press enter. Okay, and there we go. We get our answer of 16.61. Okay, now this differs to the answer that they've got on the QCAA, only slightly, and it's just due to rounding errors. Okay, so now we know that it's displaced by this amount. So the cart has travelled from here all the way over to here, and when it hits back down, it's at 16.01 metres. Or if I write this as its position vector, it is going to be 16.61 metres when it is touching 0.4, like that. So that's the point that we're using here. Okay, so moving on. Now, we're on to the last section of this, which is describing the motion of the cart. Now, when you look at the picture, you can see that we're given that acceleration is travelling this way only, meaning that we don't have to worry. You're thinking about acceleration in the I direction and acceleration in the J direction. This part doesn't exist. Now, next thing that we're going to do is we're going to work out its speed. So to calculate the speed or its velocity at that time, I'm going to integrate the acceleration function with respect to time. So here, if I think about it, I've kicked the cart, it's travelling this way. It still has no displacement in the J direction. So when I integrate this, it's just going to become a ti now. That's going to represent our acceleration multiplied by time. That gives us the speed. Okay, so lucky last thing we're going to do is we are going to think about our displacement vector. Now, it's still, well, it is technically being displaced 0.4 in the J direction, but I don't care about that. We need to integrate the velocity function with respect to t, meaning that first part is going to become at squared over 2. But this time we need to think about what's happening in the actual question again. Originally it was displaced. So if I want this cart to start over here, I need to think about it as being halfway between there and work out this distance. So it's displaced by 14.3 metres. So plus 14.3. If it was to the other side, then it would be negative 14.3. And again, like I said, I've got this here to show you what happens in the position vector, but I don't actually care about that portion. I only care about this portion. So this represents a function that has the acceleration in it. We can input the time in it, and that will tell me the displacement. Now, acceleration is the thing that I'm trying to find here, which is why I've come up with these equations for motion of the cart. So I have everything else. We know from before that it's 16.61 is where the cart ends up when the cart gets touched by the projectile, which was at 1.582 seconds. And we know that the cart is starting right of its original position by 14.3 meters. So from here, guess what button we're going to use? My favorite, solve n. So then you'll work up with A is equal to, and it'll be something very similar to 0.1, it'll be something very close to 1.86 meters per second squared. Okay, if you wanted to find the velocity from that or the speed from that, you could input that in here and do 1.86 multiplied by the time if the question was asking you to do something like that. But here it's just asking us to find the acceleration. Now, being able to do a question like this involves you having a really good understanding of projectile motion, linear motion, and circular motion. So, like I was saying in class, projectile motion is one of those things that is either going to be assessed at a very basic, simple, familiar sort of style multiple choice question, or it's going to be one of your ultimate high scorers in the complex familiar or complex unfamiliar section. So it could be a really good one to make sure that you fully understand it. Okay, projectile motion and simple harmonic motion, both of them I reckon fall under that banner.